it didn't work. Let's see if this works. There we go. Okay. No, I don't have a touch screen on this laptop. There we go. So my guys are just working on marking the midterm. Yeah, Clara. Clara, your hand is up. I don't know if you have a question. I assume you don't. That's just a mistaken hand up. So I didn't get any questions in my email. So I don't know if anyone has anything they want to ask about SN1. Otherwise, we'll work through some problems through SN1 and SN2. No worries. Okay. So as I talk about in the lecture, SN1 stands for substitution nucleophilic unimolecular. And so you might get a question like, or the following reaction. So what we're going to see in a couple of lectures is we're going to be comparing multiple different mechanisms because they're all in competition. But this is telling you this is a substitution reaction because it's there in the question. And it's asking provide the product and probably a mechanism. So this class we're meant to be talking about SN2, so you should have watched the videos up to SN2. But we didn't get a lot of SN1, so I want to do a little bit of SN1 from last class. If you have, basically you get SN1s happening when you can make stable carbocations. And we're going to see exactly why. It's not so much that the SN1 happens, the SN2 doesn't happen, the SN1 happens faster. These are all races. Everything is trying to compete. All the different mechanisms are all trying to occur, and which one can happen fastest. And if you have a really stable carbocation and you do not have a strong nucleophile, then the SN1 can normally outcompete the SN2. When can you ask questions about the assignment? Not today because the assignment's still alive. The Palladium questions are really messing you up. Yeah, we can do a few examples of that, Alyssa. That's completely fair. So we'll do a couple like that. Okay, so what we need to realize in an SN1 reaction is it's unimolecular. When did you say we get the midterm? You should get the midterm marks end of the week. I've been talking to them. A lot of them are like 3/4 of the way done marking. We'll just have to, like, you know, get out the hot poker and poke the grad students who need to finish. But probably by the end of the week. That's why I have a backdrop up. In average, this is the worst midterm I've ever seen. It's a disaster. I don't know if that's the case for every single one of you, but actually probably the people who are here listening to this and are involved in this probably did just fine on the midterm. But the rest didn't. I don't know, you guys might have done badly. The GAs are all going John, when we took this course with you years ago, the midterm was really hard. This one was really, really easy. How are the marks this bad? And I don't know what to say. I think a lot of people aren't keeping up. What I can tell you, and I'm speaking to the choir here, and even on the YouTube video, I'm going to be speaking to the choir because there are apparently still 340 or so students registered in this course. And we're getting turnouts of, what do we have? Maybe about 50 people here, probably under that. Maybe another 100 watch the videos. So we have about 150 students who are interacting with the course material. And this isn't only this, it's also the other lectures. Those have even lower numbers. So we have a lot of students who aren't actually consuming any course material at all. So it's not surprising me so badly that we're seeing course grades where they are. We shall see. I really hope that all of you who are participating had not an absolutely miserable experience. In the end, like everything else, all you need to do is end up on top of the pile. That's it. Okay, so I'm going to draw stereochemistry on this first one. Okay, so we have the bromine leaves. So this is an SN1 reaction. So the first step of every SN1 reaction, leaving group leaves. Carbocation intermediate. Nucleophile enters. So this happens I don't know. I don't think it's actually anything to do with organic chemistry. I think this is actually just a universal across all courses at all universities everywhere right now. I think it's been I understand you guys have probably gone through the worst time that anyone could have gone through in education since like whatever the 1918 Spanish flu, and a lot of students haven't developed good study habits because of that. Except in 1918, you can look stuff up online. And so I think a lot of people are really struggling with returning to, hitting coursework, especially people who finished high school under COVID. And I've done a couple of years under COVID here. This is pretty rough. Yeah, it says leaving group leaves. Okay, so leaving group leaves, carbocation intermediate forms, and now the nucleophile enters. So I guess the question I want to ask is, I drew stereochemistry in my starting material. Theoretically, you could assign R and S to that. So you're better or worse at that, depending on looking at the assignment. But theoretically, you can assign R and S to that. The product I've drawn here is, does the stereochemical information transfer? Do we keep that? Can we say anything about whether the nucleophile is coming in from the top or from the bottom? What does it say under SN1? Provide the substitution product for the following reaction. Madison apparently is, a Trant whisperer. She understands what I'm saying. You get a mixed product. I don't think so racemic. Yes, it should, Jassy. I'm just saying what we should draw it as. Absolutely. It is racemic. Those of you who said racemic or a mixed product are absolutely right. This is flat. It's a carbocation. It's sp2. We lose all stereochemistry, stereochemical information. From the starting material. So any information we had about that center, we've lost. It's gone flat. So we don't have an up or down wedge. So if we did have RRS to begin with, we now have a racemic mixture. So this was enantiomer pure. Or now racemic. Perfect. I'm just going to do a quick hydrogenation example. These are the palladium reactions that are really screwing up Alyssa. So we didn't do any of these problems in class. I think I did them in the lectures. You can look this up. What this is functionally doing mechanistically is addition of H2 across double bond. So how this happens, we actually don't precisely know the mechanism. It's just not known, but it's something like this. You have a palladium surface with a palladium nanoparticle. It's got lots of palladiums. Hydrogen gas comes close. Then there's some intermediate. Now note I'm making multiple bonds to hydrogens because I don't there it seems to be like a fast equilibrium between hydrogen gas like H2 and H is bound to palladium and then becoming H2 and then being bound to palladium. Like hydrogen only has one orbital, so it can't be both. It can't make two bonds. But it's sort of it's almost like a sigma resonance hybrid here. Because what we have is a fast, it's almost like a fast resonance between this and I'm not even worrying about what the palladium bonds are doing. I don't care. It's inorganic stuff. They got lots of bonds, metals, bond to metals. I don't actually understand how that works. I've done some work in there and I still don't really understand how metals bond to other metals. So I'm not going to pretend to understand. We don't need to understand. What we sort of have is sort of a resonance or an equilibrium. I'd accept kind of an either way to think about this. And so we have this kind of resonance structure where we have these two hydrogens separating from each other, not quite making a bond, not quite making a bond to palladium. But what we've essentially done really, right, is we've really weakened that hydrogen-hydrogen bond. These hydrogens clearly are a bit looser. And so when your double bond comes nearby, you can imagine the electrons in a double bond attack one of the hydrogens, and the electrons in a hydrogen-hydrogen bond can attack the other carbon. So you never generate a positive or a negative on the double bond carbons. They just one acts as a nucleophile and grabs a hydrogen, the other one has the hydride, the H minus, attack it. Or you can think of it as like both bonds kind of form at the same time and neither one's really plus or minus. It's a neutral reaction. And this thing goes. The new hydrogens will be on the bottom. This, I think, is where it fucks people up. Because, this is actually coming down onto a surface. And it's got a methyl group on the top. And so it's not going to attack with the methyl group that's on top coming down onto the surface. So it'll get in the way, it'll be bumpy, right? It brings the unhindered side down onto the surface and the hindered side stays up. So the new hydrogens are going to be steric bulk. If you have multiple substituents, you might need to weigh which side's busier, which side's heavier and all that. This is easy. There's a single up methyl group. The hydrogen's out on the other side. Sure, Samra, if this is really important. Yeah. Come by. I'll start drawing out the next example so we can start thinking about it. Consider this example here. And think about, for a moment, think about how that could work. This is an SN1 reaction. Which is the first carbocation you make, and what do you think the product of the reaction is? Actually, I'm going to make it a little bit harder. There we go. Try that one out. You can't read what's under the dashed H's. New H's are trans to biggest total steric bulk. There we go. Okay, give me a second. Everybody, okay. Sorry, I skipped ahead. Thanks, Olivia. Thank you, Olivia. You saved my ass. I really appreciate that. Should there be another methyl on the cyclohexane? Let me just go back and check. Shit, you're right. And it's going to be up here. That's why I put it on there so we can see it up. Okay, Faith, you're really cleaning up on these. That's your second catch. Should hire you as a proofreader. Okay, so we're moving on. Okay, that's the problem. So if I say it's an SN1 reaction, what you should probably do to address this question is see which carbocations form when the leaving groups leave. So you should compare the leaving groups first. You go, I got two chlorines. Chlorines are both moderately good leaving groups. They're not great. They're moderately good. And then I can look at what happens when the two chlorines leave. So if I get rid of the one on the bottom, I generate a primary carbocation. There's no induction. There's no resonance. There's nothing. It's a primary carbocation. If I get rid of the other one, I generate that carbocation. Is that the only descriptor of that carbocation? What else would you do, Faith, or somebody else? Resonance, perfect, awesome. Okay. Okay, and if I draw the resonance hybrid, where is that positive charge more likely to be located? Where's more of that positive charge? So on the tertiary center or the secondary center? Perfect, tertiary. Right, so we'll have a big ass positive charge on tertiary and a much smaller positive charge on the secondary. So we have the positive charge localized more on one site than the other site. And so if I'm a nucleophile coming in, I'm methanol, and I'm looking at this thing, what am I attacking? The tertiary carbon or the secondary carbon of this resonance structure? Perfect. I don't, not sure which, yeah, perfect. So everyone's coming in right. Exactly. So this is one of the, be careful, because I've always been saying, hey, things react like their second most stable resonance structure. That's true when resonance structures show real different selectivity, and we often have this kind of O plus with 8 electrons kind of thing. Here, the two things are basically identical. They're two carbocations, and what we're looking at is they're both carbocations, the same type of thing, but one has got more of the positive charge on it. So we're going to quench that because our nucleophile is going to be attracted to the place with more positive charge. It can make a bond with either, but it's going to react with the one with more positive charge because there's more positive charge. That's actually just the reason. So charge guy, then we do a proton transfer with methanol. Let's just get rid of it. And we have our product. So where the so Alyssa, where the positive charge is more, where there's more of the positive charge is where the nucleophile attacks. And I just want to, just for a second, I want to contrast that with like this situation. Because although there's maybe more formal positive charge on the oxygen, I'm fucking this up. That's in resonance. Oops, I have an extra lone pair. That what I drew there was not possible. We would react, the nucleophile here would react to the carbon, but that's because it cannot attack the oxygen because the oxygen already is using 8 electrons. It already has 8 orbitals occupied. And so we react like we're the second most stable resonance structure. And reacting like the second most stable resonance structure is also true when things are neutral, because the second most stable resonance structure tells you how the charge is delocalized. But we know how the charge is delocalized already. It's got a freaking positive charge. So where is that positive charge more likely to be? It's more likely to be on the tertiary carbon. There's more of it on a tertiary carbon. How is the D? Oh, that's just heat. Sorry, that's heat. It's a delta. How is the delta relevant in this reaction? If you don't add heat, this thing can just dissolve in methanol and swim around in there for a very long time without doing anything. Just nothing will happen. We need heat to start this baby going. Otherwise, it just doesn't do anything. So I'm going to do one more example. You rephrase the question. No, let's stick with that. So question here is which of the following here? Yeah, we'll do an SN2 next. I just want to finish off with one last SN1, then we'll start doing some SN2s. So the question is which of the following reacts fastest? A or B? And then I'm going to say this is an SN1 reaction. I didn't write that down, but in the following SN1 reaction. So, Melitza, I can't tell if you're sort of going Jeopardy on this and answering a question in the form of a question. Which is fine. So the A started with question marks. Now the question mark's been dropped and everyone's just with A. And you're right. So the question here is we're looking at these and we need to consider two things when we're doing SN1s. The nucleophile doesn't matter. You're making a carbocation, anything can react with a carbocation. It's reactive. Doesn't matter what the nature of your nucleophile is. It's irrelevant to what the nature of your nucleophile is. So what's important in the SN1, because remember when SN1 is starting material, intermediate, product, and your nucleophile comes in here. But at this point, this is the activation energy. This is the rate determining step. The nucleophile is not in the rate determining step, so the nucleophile does not determine how fast the reaction goes. It's irrelevant. What matters is how good is the leaving group and how good is the carbocation you are making. And you're trying to balance those two factors. So a really good leaving group is really good. A really stable carbocation is really important. You kind of need both. So in an SN1 reaction, so this is the SN1. And that's a good question, Alyssa. So what's going to happen is A is going to react faster because iodine is a better leaving group than bromine, and the two carbocations we make would be identical. And so it just comes down to how good the leaving group is. You know, I used to always make this gesture to express things, but now I've seen like Donald Trump make that gesture for 5 years, and I never want to make that gesture again because I feel disgusting when I do it. Okay, so we heat that. This is part of that liberal indoctrination shit that you come to university for. So we break the carbon-iodine bond. The iodine moves away. In a transition state, the bond is partially broken. This is the intermediate. by the way. It's a carbocation intermediate. In a transition state, the bond is partially broken, but the iodine hasn't drifted away completely. In the intermediate, the iodine has drifted away completely. All we're left with is a carbocation. So in the SN1 reaction, there's one molecule involved in a rate determining step. It's the starting material. And the rate is determined by how fast we break that carbon leaving group bond. That's it. That's all that matters. And the only thing that determines that is the stability of the carbocation you form and the stability of the leaving group once it's left. I minus is pretty stable. A secondary carbocation kind of sucks. Yeah, I minus stabilizes a negative charge better than bromine because it's bigger. Go back to way back at the beginning of the class. Lecture 2 or 3, we started talking about relative stability, like S minus stabilizes charge better than O minus. When you draw equilibriums, you get the S minus. HI is a stronger acid than HBr because I minus is more stable than Br minus. Then the nucleophile comes in. And it does not matter what the nucleophile is. This reaction will react the same rate if I react with isopropanol or methanol. Isopropanol, this is isopropanol, it's a lot broader. It's got a lot more steric bulk. But it doesn't matter because the carbocation is so reactive. This reaction is diffusion limited. So as soon as the two things come close together, boom, they snap together and make a bond. Which is not going to be the case for the SN2. And any stereochemical information I had going in has been lost. Then there's a final proton transfer, just to make everything neutral. We have that. I like your comment, Amanda. But it all plays into this. I'm sorry, you haven't lost it. It's just here. It's still here. When will a stable carbocation beat the leaving group? Let's go into Samantha's question there. So we have this. So let's say we have another case. First of all, carbocations are normally the worst part. Like, they're normally the least stable thing. So if we have the same question, which of these is faster? And you can say, what the fuck did I just draw? Talk about that in a second. So this is the best leaving group known to man. Think about it for a second. Now, I want to draw resonance with this. We can't because of the orbitals involved, or d orbitals versus p orbitals, and it doesn't do that. But then the inorganic chemist will quickly come and say, well, no, but the stability is the same as if it did resonance. So I'm like, why don't we just draw resonance? But we're not allowed drawing resonance. But think about the resonance that we're not allowed drawing. There's good resonance there, or the thing that is equivalent to resonance because of the way orbitals work. We also have a big CF3 group that is pulling electron density out. So besides like actually positively charged things which aren't stable, the best leaving group ever is this thing. It's also called a Triflate or a Trifluoromethane Sulfonate, but no one wants to call it that. And we often abbreviate it as TF because we love abbreviating things. Anyways, so I've got the best leaving group known to man, and I've got a chloride, which is not the best leaving group known to man. It's actually kind of bad. But the best leaving group known to man is attached to a primary carbocation. I am going to have to add in a disclosure here, though, which is faster by SN1. because we'll see that that's not the only thing we need to consider here. Yeah, Alyssa, I can go back. Let me know when you're good. Okay. Thumbs up. It's fine. Okay, so we have this comparison here. We can make a primary carbocation with the best leaving group ever, or we can make a tertiary carbocation with a moderately okay leaving group. Which one do you think is faster? I know it's hard, eh? A or B, and B's are coming in and you're all right. The difference, chlorine stabilizes a negative charge? Yeah. Does it love to? No. Can it? Yeah. Triflate stabilizes a negative charge? Oh, holy shit, does it ever. It's always wanted to stabilize negative charge. But that doesn't matter compared to the differences in carbocations. It is really, really steep from a resonance stabilized carbocation to a tertiary, then from a tertiary to a secondary, and then I'm pretty comfortable saying that primary carbocations do not exist. There have been a few examples, just when people really engineer something fancy to make it, to show it. And yes, they're very clever, but under normal circumstances, so I don't care how good the leaving group is. We could wait here for the lifetime of the universe, and it's just not going to happen. Because primary carbocations suck. Okay. Now, we talk about the SN1 reaction. Let's talk about the SN2 reaction. Yeah, tertiary will it's almost always the carbocation that dominates. The only case when it wouldn't is when there's such a huge difference in leaving group ability. Let's say it was a hydroxide leaving group versus a triflate, then the secondary would win the triflate because hydroxide is not a leaving group. So but chloride would still win in that case, Samantha. If we had that and it would have been a secondary instead of a primary, the tertiary would have still won. The carbocation really, really matters. But we'll see that that's great in theory. In practice, we then have this confusion because the SN2 reaction can take over. And that's going to compete. So I'm just going to do a really simple SN2 reaction. So in the SN2 reaction, so Drake, they're not in the plane, they're just racemic. So Drake's saying, hey, in this, for SN1s, is everything always in the plane? No, it's not in the plane. One of these is up, one of these is down. It's just you have an equal version with the other one with them switched. And so by drawing everything in the plane like this, I'm saying there's no stereochemistry here. That's a racemic center. Or it is a stereo center. Well, this one's not, because I guess these two things are the same. But there could be a stereo center there. It's just as racemic. Are there exceptions to that? Yes, and we'll see one. I think I actually put one on one of these. No, I didn't do it on one of the assignments. We'll do that in a moment. Okay, the SN1 reaction, the rate determining step was the leaving group leaving. We had to worry about how reactive the carbocation we would make would be, one as stable as possible, and how stable the leaving group would be. In the SN2 reaction, the nucleophile kicks out the leaving group. There's no carbocation at all. We form a new carbon-carbon bond. We break a carbon-iodine bond. It happens simultaneously. If we want, we can actually draw the transition state. And it goes to the product. So what matters for an SN2 reaction? How unstable is the nucleophile? The more unstable, the more reactive. How good a leaving group? That at least is the same. What would be, there's a third parameter though we need to worry about. With the SN1, all we need to worry about was stability of the carbocation and stability of the leaving group. Here we need to worry about the stability of the nucleophile, stability of the leaving group, and there's a third thing we need to worry about. Exactly, steric bulk. So if I have an example like this, they're both chloride leaving groups, so that's the same. The nucleophile is cyanide, that's the same. But if I say there's only one equivalent, which one does it react with? That's a transition state. So we have partial bond formation between the carbon and cyanide, partial bond formation between the carbon and the iodide. Well, they're both chlorines. Madison said the one on the far left. Madison, do you have problems with left to right? Yeah, and everyone else is correct. Drake and Faith and Fatima, you're absolutely right. You attack the one in the end. Why? Because it's primary. There's a lot less stuff around there. If you build a model of it, where's my balls? Okay, there's a similar one. It's not quite the same. We have two chlorines. Oh, I'm going to turn off my background because it won't fuck up with everything. Okay. So we have two chlorines on this molecule. One is on a tertiary chlorine. And so my nucleophile we're going to talk about this in a second, needs to come in directly from behind. So this is the backside attack, which has entertained generations of undergraduate students. and professors. So we need a backdoor attack from this nucleophile for an SN2. Notice that there's a lot of stuff here blocking this access. The carbon doesn't want to provide that access. Whereas for this guy with this chlorine here, we're clear, right? We don't have all these carbons around. It's just very easy for us to come in directly behind the chlorine. So this is why steric bulk matters, because there's lots of angles. There's a lot of easy access to this side. Whereas this side, we are sterically hindered by everything else that's around here. If we miss our angle a little bit, we're not going to be able to get in at that carbon. And so in this case, we would draw the arrow cyanide attacking, chlorine leaving. The arrows happen simultaneously. As the cyanide bond is forming, the chlorine bond is breaking. The chlorine does not leave first. The cyanide does not add first. As the cyanide is joining, the chlorine leaves. Okay. Let's just, I want one thing I did talk about that. So let's say my question is, so explain using orbitals the stereochemical outcome of the reaction. I'm using another really good nucleophile, sodium azide. And what we're going to do is we need that backside attack. That is what is indicative of an SN2. We're going to see why using orbitals. But what we're going to get is the azide attacking the carbon with the leaving group leaving. And then we are going to flip the stereocenter. And it's the real inversion of the stereocenter. The iodine was up, the azide's back. Why is that? Okay. This comes down to, again, talking about what is the weakest bond in the molecule. So when there's iodide off there to the left, the weakest bond in the entire molecule is the sigma bond between carbon and iodine. Everything else is a carbon-carbon bond, carbon-hydrogen bond, really, really strong. There are 2 electrons in that sigma bond. There is also an antibonding orbital for it, because of course there is. There are no electrons in the antibonding orbital, because if there were electrons in the antibonding orbital, we would break the bond. Okay, so if we think about what that orbital looks like, just going to look at the carbon itself. The sigma bond between carbon and iodine looks a bit like that. I'm just going to sketch in the other bonds. I'm not going to draw the substituents or draw the orbitals. We don't worry about that just right now. I'm just going to sketch them in. Okay. The sigma star between carbon and iodine can't move any of the bonds. Everything else is the same. We are just changing the orbital. And remember, a sigma star, a sigma bond comes because we take an sp orbital, sp3, sp2, sp. and we put one lobe, the bigger lobe, between the two atoms, because that's where we want the electron density. But it came from mixing S's and P's. There's no more chance of that lobe having density between the atoms as away from the atoms. And so the antibonding orbital of this just looks like the opposite. Oh, look where it is. It's directly opposite the bond. It's 180 degrees away. And it's an empty orbital. And it's the lowest empty orbital on the molecule. So let's say we have a nucleophile coming by. You have an azide. It's got 2 electrons in a non-bonding orbital. We haven't used this nomenclature yet, but they're just a lone pair. They are not bonding. They're not doing anything. And they're looking for an orbital to interact with because they want to make bonds, because electrons always want to make bonds. It's kind of what electrons do. And they're in an sp orbital on azide. You can imagine this orbital with 2 electrons in it lining up with this antibonding orbital with 0 electrons in it and making a new bond. The orbitals line up, right? Look, they look about the same. Like you can imagine those two coming together. So you can imagine the azide interacting with the carbon antibonding orbital. It's a star. It's a really shitty star. So you have the azide non-bonding orbital interacting with the carbon iodine sigma star, which is directly opposite the carbon iodine bond. But as soon as I do that, I'm putting electrons into the sigma star. And as soon as I do that, I break the bond. So all this is a direct result of how these orbitals interact. Every orbital always has an antibonding orbital. The weakest bond in the molecule has the lowest lying antibonding orbital. Because it's the weakest bond, you get the less energetic benefit from it. And since distances to antibonding orbitals and bonding orbitals are always the same from the 0 point, like here's not bonding, antibonding is a distance below, bonding is distance below, antibonding is the same distance above. You can't create energy or destroy energy. So if you gain energy like this, you have to create an antibonding orbital which was equal in energy and above it. And then when something interacts with that, with the lowest energy unoccupied orbital, the easiest orbital to get to, it breaks the bond. So we sever the bond between the carbon and iodine because we make the new carbon cyanide bond. And the geometry of it means that the cyanide, or the azide in this case, has to come from the back, because that is where the big lobe of the antibonding orbital is. So, like literally so. SN2 reactions occur with inversion of configuration because nucleophile must approach 180 degrees from leaving group, because that's where the antibonding orbital is. And to break a bond, we must occupy an antibonding orbital. There's a few ways you can do that. This is one way. In the SN1, there's no nucleophile. How do you occupy the antibonding orbital? You provide enough heat, and one electron in the bonding orbital jumps up to the antibonding orbital, and suddenly you have one electron, the bond breaks. But you need a weak bond to do that. Otherwise, the bond's not going to break. But SN1, weak bonds, they do it. And that's why you need to add some heat, because you need to make the electron jump. So you break bonds when electrons occupy antibonding orbitals. You form bonds when electrons form bonding orbitals. This is just the way it is. And the way that orbitals interact, orbitals have three-dimensional geometry, that determines the geometry of the partners that must interact in a reaction. Okay, I kept talking there, Amanda. Did you get less confused, or you stayed confused? I think I went through a similar discussion in the lectures. If this doesn't help you, you don't need it. I'm not going to ask you to do this, but it's important to understand why you need this backside attack and inversion of configuration. Okay, cool. I think fundamentally this matters. As much as like anything matters. But the results of this is what is really, really important. That's that you do get inversion of configuration. The nucleophile always comes front and back. And the reason it does that is because of orbitals. Mohammed asked, for the final, let's say I do better on the final, do you erase the midterm mark? Yes. Your final grade can replace your midterm grade. So whatever weighting of your midterm is weighted to your midterm, your final substitutes that. I use automatic calculations for that to determine if your final grade is better than your midterm grade. It calculates your mark. Do a lot of like logic programming in Excel. I don't. No, yeah, well, it ends up, okay, so the question, I'm going to answer Melitza's question first. So Melitza says, hey, so it attacked 180 degrees, but ends up 120. No, it ends up 180. The rest of the molecule actually folded, and we just drew it like that. Like what actually happens is the nucleophile comes in from back, the leaving group leaves, the molecule actually goes completely flat, which I can't do with my model kit, and then it kind of spins the other way. And so it sits like a cone with the way, like if the nucleophile is coming in like this and the leaving group's up here, the other three things are like my thumb, this kind of cluster of fingers, which this is really hurting, by the way, because I suck at this like a tripod. As the nucleophile comes in, this flattens out, and then it actually starts to curve out the other way to make the tetrahedron out the other way. So you start with the tetrahedron, you attack from the backside, like the awful place in the tetrahedron. The tetrahedron flattens out into a square trigonal structure, and then reforms the tetrahedron the opposite way. It's December 11th then. I don't make the rules. The university sets when these exams are, which is almost, that's right at the beginning of the period, actually. I think our last class like December 9th or something. Yes, Zane, your midterm rides on your exam. Do better on a midterm? No, the assignments do not get replaced by the midterm. The assignments stand. You drop the worst of your assignments. Yeah, there is no middle step. Like I can do this. So let's say we just have a really simple example. Maybe so I can show what I was just talking about. I'm going to redraw this a little bit. That's a really shitty tetrahedron. So let's say we have that. We can agree it's kind of tetrahedral-like. Your nucleophile now comes in. Let's say our nucleophile in this case is CH3-. It's going to attack from the back side. It's going to break up the iodine. Now it's going to go through a transition state. In that transition state, the three methyl groups are all perfectly in a plane. So the methyl group, so the iodine bond is elongating, the carbon-carbon bond is starting to form, and all three methyl groups are perfectly in the plane. It was not wise to use a methyl. I'll write CH3 for the new one that came in. And now what we've done is we've kind of opened the fan the other way. So you can sort of think of this as kind of like a triangle folded to the left, and now it's become a triangle kind of open to the right. And it's because like we've done inversion configuration because we've actually kind of like taken an umbrella and pushed it outwards backwards. Like we've opened the umbrella up the wrong way. Like normally an umbrella, covers you like this, and the wind comes up and it blows up the other way. That's what we've done with the tetrahedron. We've blown it open the wrong way. So this is a transition state. In the SN2, there's starting material, transition state, product. There is no intermediate. There might be an intermediate because something's charged. You need to get rid of a proton transfer, but there's no real intermediate like there was with a carbocation. There's none of these mechanistic intermediates. Like here, there's no intermediate because everything's neutral in the end. Starting material, transition state, product for the SN2. Compared to a lot of the arrows we've drawn, yeah, if there is a that would count as, so what we're always saying is, hey, the SN2 has no intermediates. That's a bit of a lie, because if the nucleophile had been an amine, well, alcohols aren't normally good enough. Now I'm lying a bit here because we're going to talk about this next class, but tertiary, you know what, I don't want to lie. I like you people too much. Tertiary centers do not do SN2s. They don't. Proton transfer. It's like, what the hell am I doing? No, let's do something else. We've seen lots and lots of alcohols. Say we had ammonia. Inversion of configuration doesn't matter because it's not a chiral, it's not a stereo center. It's got two of the same things attached, but still, we know it inverted the configuration. This is an intermediate because it's in a reaction and it's charged, but it's not an intermediate that's due to the mechanism. It's an intermediate that's due to the nature of the nucleophile. And this would then go proton transfer to the amine solvent, and we're done. So the energy of this guy would look like starting material, transition state, reasonably stable intermediate, very fast decline to product. So good job, Melitza. Yeah, it should be an H3+. You're absolutely right. just magically dropped one. So adding you to my notes too. Caught another mistake. Does that help, Drake? Yeah, all the assignments have been open book. They're online. I can't, all the exams are open book. Everything's open book. Just you can't talk to anybody else about them. That would be cheating. And like going to Chegg is cheating. And uploading stuff to Chegg is cheating. And other forms, because we're not restricting that to Chegg. So you can't just say, hey, I didn't use Chegg, I used like Course Hero. It's the same fucking thing. That's cheating too. But using any textbook or your notes or, you know, something that wasn't produced directly to answer the specific question is all completely valid. That's true of the final exam, but those of you, I think what's happening and what I just want to caution people about is the idea that I think a lot of people are used to, I think we're getting used to, and I think this is why the midterm marks are so low, is people are used to going, well, you know, it's open book, I can look stuff up. Yeah, you can, but if you need to look everything up, you're never going to finish the exam. So you need to know precisely where to look things up. And you need to know what you don't need to look up and what you can just put down immediately. Because if you need to look, you don't need to memorize everything, but you do need to know stuff. And you need to know where to find the information you need, and you need to know how to apply it once you've gotten that. Because if you need to look up how to apply it, you're fucked. So yeah, but I would be perfectly comfortable giving that midterm as a closed book exam. I wouldn't have flinched. It's completely fair. We would have given you some tables of A values and stuff. But there's no reason that couldn't have been a closed book exam. It wasn't written as an open book exam. And that's why I'm so depressed about the midterm. It was also written as a 3-hour exam and everyone had 4 hours, 4.5 actually. Because Blackboard. Yeah. Yes. I don't have a final average yet, Mohammed, so I don't know how awful. I do know that I was talking to the person who's marking a Newman projection, and he said that 70% of the students who had written a Newman projection one with the cyclohexane rings only drew a single circle, didn't draw 2 circles. And so the maximum they were going to get was about half, and most of them didn't get close to that. So the majority of the marks were 0s or 1s out of 6. So if you drew 2 circles, you're in the top 30% of the class on that question. Oh no, the average is not passing. Well, we don't know. It might still come out that way. I really hope it is. I don't curve the midterms. I don't curve the finals. We recalculate what the final grade is based on people who are performing best in the class for the final exam. So normally what that means is I knock like 4 or 5 marks off the final is what normally happens, and that gets me a handful of students who are getting over 100. Like if there are classes I know, especially in the British system, where, you know, in England, you get a student with a 65%, you say, yeah, it's a top student in the class. Nobody gets 100 because the questions are really, 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 really hard. And so 65, if you can get 65% on the exam, you are acing it. And so, you know, everything gets regulated to that. Here, there are people getting 100 just raw score on the exam. And so it's fully possible to do. They're not necessarily smarter than everyone else in the class. They're just trying harder. So I don't want to penalize them for the work that they put in when suddenly I'm raising and passing a whole lot of people. I think we're going to have much higher failure rates this year than general. Yeah, it's the worst. It's the worst midterm I've ever seen. But I can say that, you know, about 35% of the class is interacting with the online video materials or the courses at all. So 65% of the class have not really looked at the videos. They're definitely not attending class, they're not coming to office hours, they're not interacting with the TAs. So I'm talking to people who are attending class, right? And anyone who's watching this on YouTube, you're in a tiny minority of the class that's engaged. Oh no, the errors are not due to silly. If you make silly errors or mistakes, Madison, you generally get almost all the marks. We know it's a silly error or mistake. We give you almost all the grades. It's due to people going, "What's new in projection?" I haven't seen anything like this. What's a bond? That's the issue. So Julia, if you there are some people are getting like 80, 90. I think the highest mark so far is somebody scoring perfect on all the questions. And I think there are a bunch of those. So it's not like everybody's doing badly. It's just the majority of the class is doing badly. But I'm probably really, really talking to the wrong group of people here about this. And I'm not reaching the people who need to hear this message. You guys are probably all doing fine, to be honest. I'll be really, really surprised if you don't do well. You're trying. That's the best I can say. So thank you for coming to class, because this would get even more depressing if there are fewer of you. Anyways, enjoy your lab. Samara is not here today. She's desperately involved in something else, so I think she'll make up this meeting on Friday after class to do sort of chemistry with Samara. You might not feel like you're doing fine, Faith, but you're catching all my errors. So you're not doing badly. This is hard. This is really, really hard. And we're running and we're doing new things constantly. This is really, really hard. This is really, really hard. I don't know how to say that. There's a lot of stuff. It's all brand new. The whole freaking discipline is new. You've never done anything like this. And I've got a huge curriculum that I need to shove in your brains due to the MCATs. And for people who are only doing one of these. So it's tough. There's a reason this is considered normally the hardest class that anyone takes, unless they're really suck at calculus, in which case calculus is the hardest class they take. But calculus is easy because you've been doing math forever. At least I think so. Okay, take it easy, guys. No, you're fine. I'm Faith, like honestly, this class is fine. The interaction I'm having with you guys are the most really involved. I love it. I really appreciate you guys. I just wish I was reaching the 70% of the people who aren't interacting. Just take care. Have a good day.